Okay, for those who are already in, hello everyone. I am Luciano Pedruziello, and on behalf of the Young Researcher Activity Team of ISQG, the International Society for Quantum Gravity, I would like to welcome you to this third course, which will deal with perturbative quantum gravity. The course will be held by Professor John Donoghue. John is an emeritus professor at the University of Massachusetts, Amherst, and during his academic career, he's been mainly involved in the areas of effective field theory in general, and particular emphasis to treating GR as an effective field theory, fundamental interaction, elementary particle physics, both at a theoretical and a phenomenological level, but he's also been working on other related topics. At a personal level, let me say that I indirectly met John when I was a PhD student, when I came across his very interesting works on finite temperature field theory for the first time, where he basically addressed the equivalence principle and its possible violation due to radiative correction to the electromagnetic and gravitational couplings. And since then, I have to say that I kept following John, not only at the level of the research products, but also at the level of teaching activities, because he has excellent skills. And I am pretty confident that by the end of these lectures, all of you will agree with me. If you want to have a little bit of anticipation of what I'm telling you, you can refer to the link that you can find on our website, which will redirect you to a page which is handled by John himself. But don't get too many spoilers and just follow these lectures. Be careful. So I don't want to dwell on these preambles much. So without further ado, John, please, the stage is yours.
Well, thank you very much for the nice introduction. And thanks for the opportunity to do this presentation and have it recorded. I think it's nice that you're doing this series, and I applaud your work there. Let me share my screen. And we can. All right, there. So it's showing okay?
Yeah.
Very good. All right. So the topic here is general relativity as a perturbative quantum field theory, or as an effective field theory. And to start, let's just do a little reflection on what the point of doing this and what the status of it is compared to other theories. If we go back and look at some of the pioneers of the subject, I have something here with Feynman and Weinberg, who we were going to end up covering the material that's in both these papers. But they both have interesting starts. They're both apologetic. So one of the things you can see is here, Feynman starts off, it's hard to explain why you do any of this. But since I'm among equally crazy men, let me just go ahead with it. Weinberg also says sort of the same thing. It's difficult to pretend that this is urgent, but I'm doing it because I can, and because something might go wrong, even though nothing does. These days, it's interesting to look back on that and think of how we do it, think about it now. At the present stage, quantum gravity is one of the core topics of the subject. And so you don't see people making apologies like that. My personal feeling is that why we do it is we know that gravity exists. That there's mysteries there. Mysteries are still to be found, even though we know some things. And it's also an interesting quantum field theory with unresolved issues that needs work on that. So this is why I do it. You do have to admit that there's going to be less phenomenology opportunities, but nevertheless, it's an exciting opportunity. But then I'm presenting here, I'm doing other things also, but why do we do it as a perturbative theory? Many of the main issues actually happen in the non-perturbative regime. But the perturbative theory is really the foundation. And I think it's important that everyone understand the foundation. In particular, if I think of the world of quantum gravity, I think there's the core here is, I'll call it GR as an effective field theory. The theory I'm ending up describing here is that outside of this, they're surrounding in various directions. You could have strings, loops, causal sets, but they all have to limit down to this. If they're to be successful, they have to come back to this core. There are some that live on the boundary, like causal dynamical triangulations. So some of these other areas are making contact with the effective field theories now, but you have to make contact with this perturbative theory at low energies. The other thing is that this is the quantum gravity that happens at ordinary scales. Such that if you think about the world around you, this is the appropriate quantum gravity for the world around you. And I'll often come back to that, trying to think about the theory in connection to other types of theories. It does have some reliable predictions. These are few and far between in quantum gravity, but we might as well see the ones that do exist. And perhaps most importantly, it displays limitations. So what we know, so this boundary here is that there's some things we know and some things we don't know. The best one way to explore it is from the inside to see what you don't, where your knowledge falls apart. And I have to admit that in some ways there's a philosophical that I would like to also convey. And that's to change the thinking of, I mean, I'd like to do the whole community, but let me try on the people that are participating here first. Change the way that one thinks about gravity as a quantum field theory or as a field theory, because it's often presented as distinct, an outlier from the other theories of that we have as fundamental theories. And so you often think of that gravity is the theory of curved space-time. Other fields play on this curved space-time, but the fields and the space-time are somehow different quantities. What I'm going to try to convince you or show you is that gravity is like the other theories. at ordinary energies. So ordinary energies require some quotes. I used it above too, because that's explaining what that means is part of the mission here. So in particular, if I think of the theory of the world, this is how if I was to write down the laws of physics. Here's what I write. I write a path integral over the fields, and here I'm going to include the metric. The path integral is done with the exponential of some action. And the ingredients here are there's kinetic energies and interactions. There's fermions. There's, I'll skip the Higgs, but let's put in the gravity. And most importantly, this has some caveat that there's some limitation. The theory of the world, even for the fermions, for the electrons, changes this with scales and maybe is different at very high energies. So, but if I think of the theory of the world, I need to put this metric in the path integral. If I do that, I end up having a full quantum field theory. And so I'd like to convince you that the structure is basically similar to other theories within some limitations. Okay, so there's my goals. Let's do some bookkeeping. It was mentioned that I have a website. The websites, I have two that you might think about. This one here is the website for the course. It's listed on the web page of the series. I will post there references, lecture notes, links to the recordings once they're available. So you can use that as a resource, hopefully, for things. Notes should go up there pretty quickly. Other bookkeeping items. One is I use the metric. So this is a perhaps for I use the metrics, which is mostly plus, because I come from a particle physics background, and that's the typical particle physics things. So for some people that might be difficult, but I think you can translate the basic ideas anyhow. There are some references that I might suggest. So let me just copy these and stick them in there too. So there's a series of notes that I gave in 2017, which I will follow somewhat here. And so you can see some of this material presented there with formulas nicely typed out instead of handwritten, etc. So this is on the web. You can find that. I also would like to highlight my own book because I use this material over and over again. This from the book, The Dynamics of the Standard Model. This is now available for free. Okay, it's an open access book. You can download it for free. I'm actually very happy that we've done that. The link to that is on the webpage, and so you'll see a link that lets you go and get that book. And I use that for some of the effective field theory stuff. I use it for heat kernels. I'm going to talk about heat kernels and the like. The other book I highlight right at the moment is Gasparini's Theory of Gravitational Interactions. Things I think are useful in is it has the formulas in the metric here. So if you want to see the formulas for many of the aspects of general relativity in the metric that I'm using, it's in there. Because of that, I use many of the conventions there. And it's also one of the few places that I know that does fermions well. And I'm going to, as you'll see today, go through that. Let's see. There's also, I'll just the other books to highlight. These are just advertisements. They're not as completely as relevant, but I do like Matt Schwartz's book on sorry, let's get rid of this. Matt Schwartz's book as a background reference on quantum field theory. He has some of the techniques that I use in there. And then, of course, there's always Weinberg as a great reference who's compatible with this approach. Okay, if there's anything else I should say, otherwise I'm going to start. The plan is to start doing constructing general relativity as a quantum field theory, quantizing it, calculating, and presenting some useful techniques along the way. Okay, so there's and I guess I should say that there's going to be these 3 lectures in June, and then the rest in August. And we'll see if it's 3 or 4 more in August. Okay. Anything else I should say is preparation that anyone wants to hear? Okay, let's.
May I review?
Yes.
Will there be any problem state to work out or something?
There can be. I haven't planned it out, but I do have some problems I've used in this setting before. If people would like that, I can add some. I mean, one of the things I do routinely do is there are some places where I'll say you should work this out on your own for an exercise. But then I do have some other problems. I guess I can add them if there's interest in doing so.
Yep.
Okay, good. The other thing I should say is that as an initial exercise, everyone should go off and read Feynman's paper. Okay, Feynman's paper is already on the website, but it's a fun paper. It's historically important because it is the place where gravity was quantized correctly the first time. Okay, so he does the perturbative quantization of gravity correctly, where he introduces what we now call today Popov ghosts, but really should be Feynman DeWitt today of Popov ghosts, because Feynman produces them here. The other thing that's interesting about it and fun about it is that it wasn't actually written as a paper by Feynman. It was a transcription of a talk. And so it's written in, you can hear Feynman's voice as you go through it. It's not, perfectly written out. It's Feynman talking to you. And you can sort of see it even here, so, but since I'm among equally irrational men, I will not be criticized. And so you hear him phrasing it, and then there's also a question answer period with Bryce DeWitt hearing this for the first time. You can hear him realizing something important has happened, and he's trying to probe Feynman on this. And maybe as we get to the right point, I'll show some quotes from that, because it's a lot of fun. Anyhow, first assignment is go read that. Okay, so let's try to think about a theory for gravity. And let's think as particle theorists might. You might try constructing something that looks like E and M, because you have the gravitational potential looks like the Coulomb potential, but doesn't work. You can't do spin 1 because spin 1 always comes with opposite charges. So it has to be spin 0, spin 2, or higher spins if you want, but spin 0 exchange would be always attractive. And so that's a plus. And if you did it, let's imagine you made a coupling. The Lagrange was, some minus m psi bar, some coupling, let's go kappa psi bar psi phi, this being the scalar that's being exchanged, and you made a potential like with phi exchange, this would be kappa squared over 4 m1 m2 particle 1 particle 2. You'd get 1 over r, and you if you identify this with G, you could make a nice theory that looks almost like the Newtonian potentials. And in fact, this would work as it would build the Earth, it would build suns, it would build many things, but it fails only through some subtle features. It fails because of Etfish. Etfish shows that the gravitational masses and the inertial masses are the same, but that includes things like binding energies. When you measure the inertial masses, that's not the sum of the individual masses. And so if you made this the particles' masses, it wouldn't work for composite particles like nuclei. And so it would fail the equivalence principle tests. So it's somewhat subtle, but it's nevertheless true. And also it fails because of bending of starlight. The couplings for massless particles would be something like the f squared, which vanishes because e squared and b squared are the same for light. So it would not lead to bending of starlight. So the scalar theories don't work, but for somewhat subtle reasons. But they do tell us something that we do want to build into the theory, is we should use the total energy. And if we're going to use the total energy in a relativistic theory, that implies energy and momentum, and it implies that that we should be using the construction that's the energy momentum tensor. So let me just briefly make that connection. The energy and momentum tensor and energy and momentum come up from space and time translations. So if there's a symmetry, the symmetry is x goes to x mu prime, which is a shift of these variables by constants. That shift then gives us, if the Lagrangian is invariant under that, Noether's theorem then tells us Noether tells us that there's a conserved energy momentum tensor, which is defined by the derivative of the Lagrangian with respect to d mu phi minus eta mu nu Lagrangian. And if I take, so there's a conserved current, there's a conserved charge, which is the energies and momentum, and this is also conservation law, d mu nu equals 0. If I'm doing for a scalar field, the Lagrangian is the usual Klein-Gordon Lagrangian, and T mu nu that follows from that is d mu phi minus eta mu nu over 2 d lambda phi minus m squared phi squared. And here's one of the exercises that you can do. You can try, you should test the conservation of that. Of course, it works. And maybe at this stage, I'll even put in something that's going to be the start of our Feynman rules. So this is the energy momentum tensor. When I take its matrix elements, P prime, T mu nu, P is the matrix element. these derivatives here act on the field, and they get p mu p prime nu, but it's symmetric. P prime p nu minus 8 mu nu over 2 p dot p prime minus m squared. Okay, except that, remember, this is supposed to be the energy. The states actually carry a normalization, so let's, for convention, do the normalization. P prime p equals 2e delta 3 of p minus p prime. And so if I am taking this matrix element, there really is also a 1 over 2e prime sitting out there from the normalization. When we're going to do Feynman rules, if you remember your construction of the Feynman rules, we drop these. So that the matrix element that you'll see in Feynman rules is this one that carries the dimensions of energy squared, even though the T mu nu is the energy momentum tensor. And if you then go to the limit where these things are at rest, it is just, this reduces to just the mass. Okay. So there'll be occasions where these factors out in front need to be taken into account, and occasions where it doesn't. Okay. Okay, so there's our energy momentum tensor. The question is now, so we've determined by looking at Edfish that we want T mu nu as the sources of gravity. Okay, so the goal is to construct a theory. And so what I'm going to do right now is go through the gauge theory construction, because we're going to construct it as a gauge theory. And the simplest case that we know and love is how we construct all our theories. We identify the source. And so let me here to use QED as an example. We know in QED that there is a conserved current J mu, and that this is associated with an invariance. The invariance is psi goes to e to the I theta psi. And if that's an invariance of the Lagrangian, we have a conserved current. And if you multiply that by the electric charge, the conserved current is E psi bar gamma mu psi. So if we want that as the source, our construction is that we turn this into a local invariance. Okay. We say let's let psi goes to e to the I theta of x times psi. Now that's not going to be invariant because the Lagrangian is not invariant under that. So we have to make a change to covariant derivatives. I d slash minus m psi is invariant. D mu, we have to add an extra ingredient, becomes where we add this extra field, the gauge field. And that's added in such a way that d mu psi goes to e to the I theta of x d mu psi. So in other words, it transforms this the same way as the field itself does. And then this is possible if the gauge field transforms itself. In a particular way. And that leads to the invariance. This is the gauge invariance. And then we construct the theory by noting that d mu d nu commuted with d mu d nu acting on psi is invariant because the derivatives are themselves, ends up looking as it's i.e. f mu nu psi, with f mu nu being in this case d mu a nu minus d mu a mu. So that this in turn must be invariant. And we can then easily form the Lagrangian. Okay. And there's QED. We're basically going to try to construct general relativity by saying the same words. Basically going to go the same direction. Before I do that, I'd like to just introduce the non-abelian notation because it is much closer to gravity. If I have a group SUN, I have the fields having n values, and the invariance is this n component field going to u psi, u is the exponential of e to the minus I some alpha times some matrices, or the issue, those are the issue 2 matrices with some structure which I don't think I'll bother writing down. Presume we know it, but the construction goes as follows. Since we want psi, we're going to make this a local. Sorry. We're going to have psi goes to u of x, where that's a function of position. Psi, we will want to have a covariant derivative, which goes to u of x d mu psi. D mu is d mu plus ig, some coupling lambda a over 2a, some gauge fields. And if I'm trying to make the notation as nice as possible for you, everybody, this is d mu plus I G A mu, and I put double bar under that to say that this guy is a matrix. So it has 2 indices on it, or it has 3 indices. There's the matrix indices, and then there's the spacetime index. This can be an invariance if a mu goes to a mu prime, which is u a mu u minus 1 plus I over g. Let's see, make it d mu u minus 1. So this is the equivalent gauge transformation, and it's these are all underlined because they're matrices. And f mu nu is defined by let me just excuse me. We define these things by d mu on psi equals g f mu nu as a matrix on psi f mu nu. Let's see if I can. F mu nu as a matrix is d mu a nu minus d mu a plus I G a mu with a nu. And so all this work is mainly to get that commutator in there. The invariance is then that f mu nu prime is u f mu nu u minus 1, and the Lagrangian trace f mu nu is invariant. All right, so that's just a slight detour because but I want to use the same notation. Basically, this notation here, all those are matrices, is a 3-index equation with 2 of them being the symmetry variables and 1 being the space-time variable. So our goal here now, given what we've said, is we're going to try to construct this construct a theory by gauging space-time translations. So the goal here is just overall, we're going to take the global transformation x prime mu equals x mu plus a mu and make that into a local. So it's x prime mu equals x mu plus a mu of x. If a mu is arbitrary, this is just some x prime mu of x, basically some change of variables. That's the invariance that we seek here, and we're going to then look for covariant derivatives. Covariant derivatives are going to involve other fields. Which in this case could be the metric as a field, and at some stage soon I'm going to have the spin connection being a field. So there's going to be a matrix field that's similar. We're going to do commutators. Going to give us our curvatures. And we'll then do invariant actions. Will be the Einstein action. And hopefully at the end of the game, we're going to get some equation in motion such G mu nu that the source of gravity is the energy momentum tensor. And of course, this works, but it seems a bit crazy at the start. But if I do a construction like this, it's very similar to the way we construct other theories, so I think there's a value in doing it that way. This seems crazy. To think that doing this will give you a theory of gravity, but it might work. And of course, it does work. And the best way to motivate why it may work is these pictures, this Einstein elevator. Which is basically that the equivalence between the gravitational field around an object when you're at rest and if I put this elevator in in free fall, this then feels like an inertial frame. Feels like there's no gravity. And so the equivalence between the change of coordinate frames here of in this frame there's no gravity, in this frame there is. So this whole picture of the equivalence principle. The equivalence of a change of frame. The third picture that I should draw here is one if I had no gravity, but I have an acceleration upwards. It then also feels like a gravitational field. So in some sense, the changing the coordinates in gravity can work. And so maybe by changing the coordinates, by allowing them to be general coordinates, we can get a theory of gravity. Okay.
May I have a question?
Sure.
Yeah, so like, what is the physical motivation why we see gravity as a non-abelian gauge theory? Because I can understood that there we can define using the commutator, we can define the curvature tensor. Is it the real reason why we are actually thinking that way, or?
Excuse me. So the construction here is what I'm trying to do is use the same logic that we use to construct other theories to construct a theory of gravity. And it's not obvious ahead of time, you know, at the stage where I made the summary here, it's not obvious that it's going to work, right? One has to actually pull it together and see if it does work. But nevertheless, if we're following our nose about the way we construct our other theories, this is the way we would at least try. And then this argument here using the equivalence principle is an attempt to say that maybe it might even work. It gives us hope that maybe there is something connected with changes of coordinates and gravity. So it encourages us to proceed. So at this stage, I wouldn't say that it's obvious or there's anything intuitive about it, except that we know how to construct other theories. So I'm proposing we should try this. Mm-hmm. Is that enough satisfaction for the moment?
Yeah.
Actually, the time is going quickly. Is there anything else that would like to be asked at this stage? Because at this stage, I'll start doing it.
Okay, if you can look at the Q&A questions, there are 2 questions. Well,
okay.
If you want to reply now.
Okay, I can take some questions now.
Okay. So do you want to read them directly? I mean, I guess you have your own device, so.
I don't see them, I'm sorry.
Oh, sorry.
I'm not seeing a question, so.
So you cannot look at the Q&A question. Okay.
So on my screen, I see a couple pictures in my own screen.
Right.
I don't see the equations.
Okay, I can read them for you.
Yeah, that would be good if you would.
Okay.
Thank you.
Okay, one is logistic question, let's say, because Ashwin asks, are we going to look at lower dimensional non-perturbative gravity models?
No.
This is a curiosity, I guess. All right. So the second question instead is, what about considering Lorentz transformations? I assume that due to local translations being general variable transformations, Lorentz transformations are covered.
Yes. Yes, and so the answer is yes. The full set of invariances is it's really the global invariance is x prime mu is some Lorentz transformation x nu plus a mu. Okay, and so we could say that we're gauging this. You end in the same place if I made this a local transformation. It's basically the same thing, because this is just some new coordinates x prime that were a function of x. If a mu is general enough, if it's completely arbitrary, it includes the Lorentz transformations also. So yes. Perhaps that would have also been a fine way to present it.
All right.
My motivation for doing it, just saying it the other way, was mainly because I know that this translation is associated with the energy momentum tensor, and so I was trying to emphasize that.
Okay. All right. So for the moment, it seems that there are no other questions, unless there are some raised hands. But Sadesh, at any time, if you want, you can intervene and let
Okay.
somebody.
If you see a question that deserves to be asked at a given time, please read it for me.
All right, sure. For the moment, it's okay. I guess you can move on.
Okay, so let's quickly move on. The equivalence principle tells us something that we'll end up using. Tells us that there is a coordinate system here where there is no gravity. In some coordinate. So in this set of coordinates, we can just, at least locally, just use the usual flat space metric tensor. But if we want to have an invariant theory where we can't use those coordinates everywhere, and so there's other coordinates that are related to this, but let's in this, okay, let me write the formula down. In this case, the invariant distances are eta mu nu. Actually, let's keep this right notation right. The AB d y a d y b. If we change coordinates, and want to keep distances invariant, we would need to excuse me. if we want to change coordinates, we take some change of variables from these coordinates to some other coordinates, keeping the distance invariant tells us that we have metric G mu nu variables. And that this these new variables, then the invariant distances are written with this metric. And that if we change coordinates, so I'm going to introduce some notation here. So dx mu prime is some j mu nu dx nu, which is a function of x, where j mu nu is just the change of variables dx prime dx, and the indices are, you get them right, mu nu. There's an inverse j minus 1 mu nu is dx mu dx prime, then written d s squared is g mu nu dx nu equals g prime mu nu dx prime mu dx prime nu. G mu nu then has to transform like j minus 1. Let's just write these here and write the indices in a second. G, it's a G prime alpha beta. Let's write that more clearly, excuse me. Is related to G mu nu by this transformation. Okay, so the notation I'm going to end up using is these J's, which are basically the symmetry transformations. They're local transformations. And so I'll sometimes just write this quickly as x prime is equal to jx. G is j minus 1, g j minus 1. If I am dropping indices, which I sometimes do just to make certain points. All right, I'm going to skip some boring technical details because the time is not doing particularly well, but let me write now an invariant action out. If I want to write an action out, I'm going to use a scalar field phi of x, where phi prime of x prime is phi of x. The action all right, so I did skip some important technical details, but is written as g mu nu d mu phi minus m squared phi squared. One of the technical details I skipped is that this invariant volume element is involves the square root of g there. The fact that the derivatives times a metric tensor is invariant follows from the work that I did there with the metric tensor, and m squared phi squared is obviously invariant. So basically this is invariant because phi goes to phi, d mu phi goes to j minus 1 of phi, g mu nu goes to j g mu nu j, and that term becomes invariant also. So I've at this stage, if you grant me the technical details here, which I've skipped. The details have been about g mu nu upper and square root of g. Maybe I will write those out before I post these notes. But the point is, I wanted to very quickly get a success. We get an immediate success. Okay. If I have my action being what I wrote there, d4x square root of minus g, g mu nu, d mu phi minus m squared phi squared, and I look at the variation of the action respect to g mu nu. Okay, if I do this variation, I get two terms. I get the first piece, which is going to be d mu phi, d nu phi, and then I have to vary the square root of g, and that was in my technical details that I skipped. G mu nu times g mu nu. The immediate success is that varying this Lagrangian gives me T mu nu. And so we can hope then if we can hope for an equation where we find S is the gravitational action plus the one I just wrote down there. If I look at the variation of S with respect to G mu nu, I get variation of the gravitational action with respect to G mu nu plus T mu nu, where this is the variation with respect to of the matter action. This then gives us our hope is that the variation of the gravitational action can be sourced by T mu nu. And so our original goal that the energy and momentum will be the source is actually fulfilled. Okay, there's a little technology, and maybe I shouldn't skip over this piece here. Okay, the things I didn't say is that I define an inverse the upper indices is defined as an inverse, and so that the variation of G nu G nu alpha is equal to 0, since that's just a constant. And so the variation of G mu nu lower is G mu rho G nu sigma delta G rho sigma. So upper indices and lower indices vary by a minus sign because of the inverse property. And I'll just say a delta square root of minus G, delta G mu nu is minus square root of minus G. Times 1/2 G mu nu. So those were used in that. Okay. Let me do the matter equations motion at this stage. We'll do gravity next. Again, the action is given by the usual equation, but made covariant. If I vary this with respect to phi, I get the equations of motion for the field. You can sort of see how it's going to work out. There's a variation in respect to phi that comes from the constant term. And then there's the derivative interactions. It becomes then 1 over the square root of minus g d mu square root of minus g mu nu d nu phi plus m squared phi equals 0. Okay. This is the equations of motion then for this field given a given metric. We're going to write this as d squared plus m squared phi, where this is going to be a covariant derivative. But we'll come back to that. At this stage, I want to do something else instead. I want to preview. So that's what I wanted to get there. But I want to preview a second success. And that's to make this the claim that this looks like gravity. Okay, so the first success was that I get the energy momentum tensor as the source. The second success is going to be that this has the same properties as gravity does. And for this, I'm going to need something that I haven't shown yet, that G00 is normally 1. It's now going to be in weak field limit. It's going to be something else. It's going to be the gravitational potential. Where this gravitational potential could be, for example, so a function of x, could be g m over x minus x 0. If I had a particle located at x0, here's the gravitational potential outside of that. Or it could be gz if you're the gravitational field of the Earth, etc. And my goal here is from that input here, just that there's a small deviation from unity. I get the Schrodinger equation in a gravitational field. Okay, so I'm trying to tell you that this looks like gravity. And so basically what I'm going to do is the non-relativistic reduction. I'm going to say that the field phi that we started with looks like e to the minus I mt times some psi of x t. So I'm pulling out the fact that there's a big energy dependence with a big mass t. And then I look at the resulting equations. They've got 1 over the square root minus g d mu square root of minus g mu nu d nu plus m squared phi equals 0. Okay, the thing to note when doing a non-relativistic reduction is where the masses go. A factor of the e to the minus the mass. And so those are the very big things. The derivatives everywhere else are small things. And so if I look at this, I'm going to get, if I pull the e to the minus imt through, I'm going to get things like G00 minus m squared from the acting on the e to the minus imt with the 2 time derivatives. I'm going to get minus 2 im times d by dt. I'll get acting, so this is all going to be acting on psi of t. I'm going to act with time derivatives squared acting on psi of t. There'll be derivatives on g, and there'll be minus gij del squared, and then there's an m squared. And let me put some brackets somewhere here that go the second set of brackets. The say that the relevant approximation here is that the only thing I need to keep is the m squared phi g piece that I told you about above. Everything else is small. That's the biggest piece. So then if I look at the G0, there's a unit piece, the m squareds cancel. There's the m squared phi g. So the equation of motion that I get is m squared times 2 phi g. And I get, and then every small, I get 2 d by dt. I get minus del squared psi of x and t equals 0. And then I'm dropping small pieces. You can see that I can easily rearrange this. I now get the Schrodinger equation I d by dt of psi of x and t is minus del squared over 2m plus m phi g psi. This little construction that I've done gives me the Schrodinger equation as a success, and it gives me the equivalence principle also here. That the gravitational mass, so let's just say mg is equal to m inertial. The same mass automatically enters the construction in both places. So by doing this little construction and not doing much work at all, I've got the properties of the gravitational interaction already. I've also got the force law. if I have the Hamiltonian is p squared over 2m plus m phi g, and I want then no, the i's have canceled, del phi, just from doing typical commutators, and it's del m phi. And then let me just preview the third success, and then I'm afraid I'm going to have to stop. So we've seen that the source is going to be the energy momentum tensor. We will end up deriving a Feynman rule saying that the coupling is going to be some constant, which we'll call kappa over 2 times the matrix element of T mu nu, which we've already seen what this matrix element looks like. This looks like P nu we've seen that before. We will get so the piece that I have to pull up at this stage is we haven't yet gotten the propagator, but this is going to be 1 over q squared times some tensor. And in the non-relativistic limit, then we're going to get real QFT, T mu nu up here, T mu nu down here. It's going to become kappa over 2 squared. The limit as you go to zero momentum of this is 2e squared. So it'll be 2e1 squared, 2e2 squared over q squared. And remember, I worked to show you that there's these normalization factors, square root of 2 over 2e1, 2e2. This then limits the non-relativistic limit to some let me one step do that plus the Fourier transform. Fourier transform of 1 over q squared is, this gives 1 over 32 pi m1 m2 over r. We'll identify that with g, and we're going to be home. So this is now a way of getting out the Newtonian interaction with real QFT. And all I have to do to get that is get these Feynman rules, the 2 Feynman rules that I have here. So it's looking like this technique will be a success. All right, so at this stage is where I should pause. It looks like I'm going to have to stop. But let's take questions now. And then clearly the next thing I do is I have to construct the gravitational side and show that this gives you the full general relativity. And from that construction, we then start pulling out the Feynman rules. Okay, so it's clear that my goal in proceeding at this stage is I didn't get as far as today as I had hoped to, but in the 3 lectures that I'm doing in June, I'm going to insist on making it through the quantization of gravity. So I'm going to quickly go to the gravitational action, get the Feynman rules, and then quantize gravity using the Faddeev-Popov techniques. So that's my construction from now on. Okay, let me take questions, then we'll call it a day.
Okay. All right. So let's see. Okay. I don't know if Sadesh can help me at this point if he can look for,
There's already someone raising their hands in the participant list.
Okay. So yeah, I guess Satish has the privilege to let him speak. So
yes, I've allowed to speak now. Yes.
Okay.
Hello. Thanks for the great lecture. I have one question because I'm a bit confused about this non-relativistic limit and the Schrödinger equation.
Yes.
It confused me because it seems to imply that we start out from the relativistic equation for a scalar field and then end up at the equation of the motion for a Schrödinger wave function. And so a relativistic field is something completely different interpretation-wise than the Schrödinger wave function, or I'm mistaken?
No, so the solutions of the relativistic equations should go in a certain limit to Schrödinger equations. And so this is in both cases, it's a scalar field. There's no spin involved, but it is intended, just like you said, actually, is that the non-relativistic limit of the Klein-Gordon equation will give you the Schrödinger equation.
Okay.
And, because if you had a massive scalar object and you look at it at low momentum, you should get the Schrödinger equation. And this technique here of this non-relativistic reduction, by pulling out the major time dependence, will work for both scalars and fermions. And so you've probably seen it for fermions, getting the Dirac equation down to the Schrödinger equation. This is the same trick, getting the Klein-Gordon equation down to the.
Okay, perfect. Thank you.
Okay.
Okay. So I see another raised hand. Yeah, I guess that Sami can now speak.
Yeah, hello. Thank you for the presentation. I have a question on this line, on this Schrödinger equation. I don't understand in which sense you recover the equivalence principle, because now it's impossible. I mean, the mass explicitly appear in the equation, so the solution will explicitly depend on the mass. So now the dynamics will depend on the mass, which is not the equivalence principle.
Okay, so the equivalence principle in this sense is that the mass that enters the gravitational interaction here, if you call that the gravitational mass, and the mass that enters the kinetic energy, if I call that the inertial mass, that those are the same quantities. And this came about because the equations, in fact, only used a common mass there, and everything else was unchanged. The equivalence principle comes also again at the stage where P dot is proportional to M, and in the non-relativistic limit, of course, P is MV.
Mhm.
And so this then says that the so P dot is MA, and this then says that A is the to the gravitational potential with no factors of M. So P dot is the inertial mass times the inertial mass. This is the gravitational mass in the potential. So the inertial and gravitational masses being the same says that the acceleration is independent of the mass.
Okay, I see. Thank you.
Thanks for the question.
Okay. So let's see.
I think there is still one raised hand.
Yeah, but I guess it's still Sami.
It's Sami already answered.
Yeah. Already asked the question. All right. So, okay, there are no questions in the Q&A and no raised hands. So yeah, I guess that for this first lecture we can call it a day. Okay, so John, I'd like to thank you again.
Okay, well, thank you. And next time Feynman rules have to appear next time, and then we have to do Fedea Popov. So we have
All right.
an agenda set up for the rest of this month, and then we come back in August and do effective field theory.
Great.
Okay.
Sounds
Good.
All right. Nice. Very nice. So see you next time, which will be it was June the 14th?
Next Tuesday,
Next Tuesday. Great. Okay.
June the 13th.
13th. Yeah.
the 13th, and next Tuesday at the same time, same station.
Exactly.
Okay.
Don't forget to tune in.
Yes, tune in, please.
Thank you again, John.
Thank
Yeah,
you.
thank you.
See you next Tuesday.
Yep.